The following content is provided under 4D Science Group.
Complex numbers will not really be afforded that much attention in the lower level courses, but when you get to 266 and on 4th, maybe in some electrical engineering classes or something like that, you see that complex numbers has its applications. In fact, it's applicable to any type of heat flow, fluid flow, electrical dynamics, any of that. So, and before we even get there, we have to understand properties of complex numbers. The first of which is that whenever you take the nth root of any complex number, even a real number, there's n amount of nth roots. As you will see in this example, that there's 3 third roots of 1 plus 3i, or 1 plus radical 3i. To get there, we denote a complex number, z, such that z to the third is 1 plus I radical 3. Now, of course, z is rewritable in terms of r e to the I theta, where r and theta are real. 1 plus I radical 3 is also rewritable in this format. It would be wise that before we begin the problem, that we go ahead and rewrite this into that format. You know, this 1 plus radical 3i is another radius, e to the I times another angle. To find what the radius is, it's always the modulus, or the distance away from 0. In complex numbers, that just means the distance away from the origin, or just the absolute value of 1 plus radical 3i, which is radical 1 plus 3, or radical 4, which is 2. So this is 2 e to the I. Now what you notice is that e to the I theta, as is provable by a Maclaurin series, is cosine theta plus I sine theta. If you're taking 166 right now and you're in if you're at the end of chapter 12 where they cover Maclaurin series, just plug in I theta in for x and out will come here, this formula, which means theta is then tangent inverse of the imaginary part over the real part. This notation, imaginary part, just simply means this guy, or more specifically, this guy. The real part, RE, means this cosine theta, or 1. So that means our angle is tangent inverse of radical 3 over 1. And then after some calculation, you will see that this is just pi thirds. Reason being is because the sine of pi thirds is radical 3 over 2, and cosine of pi thirds is just 1/2. Therefore, the tangent of them is radical 3. And another property of complex numbers is because of the property in trig where you can just add 2 pi to any angle and it will still have the same trigonometric properties, so must you be able to apply 2 pi k to the argument, the angle of z, and still get the same values, where k is some integer. Rewriting z as r e to the I theta down here, we have r e to the I theta cubed is this 2 e to the I pi thirds plus 2 pi k. This left-hand side simplifies to r cubed e to the I 3 theta. And this is equivalent to r cubed cosine 3 theta plus I sine 3 theta. This side is 2 e to the I pi thirds plus 2 pi k. Now, of course, since r and theta are real, we can just compute the real parts. This 3 theta equals pi thirds plus 2 pi k. And 2 equals r cubed. And 2, well, the r is just the cube root of 2, and the theta is just pi ninths plus 2 pi thirds k, k being an integer. And of course, as you observe, if k is any bigger than 2, let's say if k is 3, you have the same roots over again, so there can only be 3 roots. So k must be a subset of I, or an element of 0, 1, 2. Which means, if you plug into this formula, that r z equals r e to the I theta, you see that z1 is just the cube root of 2 cosine of pi ninths plus I sine pi ninths. z2 is, okay, this is z1 with k equal 0. z2 is with k equals 1. z3 is equal to k equals 2. With that knowledge, we have cosine of pi ninths plus 2 pi thirds, or cosine of pi ninths plus 6 pi ninths, or cosine of 7 pi ninths, plus I sine of 7 pi ninths. And the third one is equal to cube root of 2 cosine of pi ninths plus 4 pi thirds, or cosine of pi ninths plus 12 pi ninths, or 13 pi ninths, plus I sine of 13 pi ninths. And of course, you can leave it as is, as that would be the most correct. Or if you really needed a decimal approximation, you just punch it into your calculator. This concludes the complex numbers tutorial.